Assalamualaikum warahmatullahi wabarakatuh. So today our group will be presenting our project title FEA Analysis of Commuter Bicycle Frame Design for the subject BMKT3453 Computer Simulation under Dr. Wahyono Sabto Widodo. So my name is Muhammad Zulhilmi Muhammad Kamal, and with me are Muhammad Afif Najmi, Muhammad Moizuddin and Muhammad Anik Lukman. Okay, so we go to the introduction. Bicycle frame are integral component of a bicycle that support the rider and transfer mechanical energy to the wheels. This means the frame hold the rider weight and carries the force from pedaling to the wheels. Is the core part that keep everything connected and working. Then their design must balance strength, stiffness, weight reduction and durability under various cycling conditions. In simple terms, the frame needs to be strong enough to handle stress, stiff enough for efficiency energy transfer, light to reduce effort, and durable to survive long-term use, especially under different road conditions. And then the last one is FEA, which is finite element analysis, is a tool for optimizing frame design and predicting performance under stress. So FEA is a simulation tools. It allows us to test how the frame will behave under different loads without building a real prototype. This will help us improve the design earlier and avoid failure later. Okay, now let's talk about the problem statement. So the main challenge in bicycle frame design is to reduce weight without compromising on strength or durability. During real world use, frames are subjected to several forces, which is such as the rider's weight, pedaling load, and vibration from the road surface. If not properly designed, this can lead to crack and fatigue failure, especially in critical area like the top tube. And as shown in the figure here, both integral and external cracking we are observed in the previous study. Okay, now our objective for this project is first to design a 3D model of commuter bicycle frame using CAD tools, which is we will use SolidWorks. And then the second is to perform finite element analysis, which is FEA, to simulate and analyze the frame structure. And then number 3 is to evaluate the structural integrity of the frame under simulated stress condition and suggest improvement.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Moizuddin bin Shahruzi. My contact number is B09221031. Today I will present the first slide is literature review. Let's look at why the study is important. Review research, for example by Thomas Key in 2020, found that steel bicycle frame are quite strong but can suffer from figure failure, especially at the welder joint where the stress concentrate the most. This skirt usually developed after peak loading cycle. Other study by Sheikh in 2024 compare carbon fiber and aluminium. Carbon fiber has a excellent strength to weight ratio and describes stress well, making it a great for support bikes. However, it is very expensive to produce. Aluminium is cheaper and lighter than steel, which is why it is very popular. But its well joint can still be weak and develop crack over time due to repeated stress. So, however, bicycle designer face challenges such as the most balanced weight, cost, and figure resistance to make a good frame. This is why we choose to use FEA. It allows us to model the stresses virtually before actually building a prototype. That save time and money and help to make better design choice. Next, let's explain our methodology in more detail. First, we create three design concept to compare, such as concept 1. The name is straight tube frame. This design uses straight tube connected in a simple geometry. The main advantage is simplicity, making it easier and cheaper to manufacture it, especially for mass production. Straight tube also easy to cut well and during the assembly process, reducing production error. However, because of its simple shape, this design may not discharge stressing efficiently, which can make it more vulnerable to crack at joint under repeated load. Still, it remains a practical choice for low-cost everyday bicycle where manufacturing cost is the main priority. Next, go to the concept 2. The concept 2 name is curved tube frame. In this concept, the bicycle frame include curved or slightly bent tube. The shape help to better distribute stress throughout the frame, reducing the concentration of stress at a single point. Curved tube can also absorb impact more smoothly, which make the ride feel more comfortable. Besides that, the curved profile improve aerodynamic by reducing air resistance, which is especially useful for performance or sport bicycle. However, curved tube are harder to manufacture and may cost more due to the forming and precision needed during the production. And the last concept is concept 3. The name is addition font tube and for chill seat. This concept introduces a special extra tube at the front of the seat area. The purpose is to create a stronger support structure if a child seat is installed. It helps maintain balance when carrying additional passenger like a child by distributing the load more evenly. This reduces the risk of tipping over having the frame deformed under extra weight. The design keep a step to styling, which mean it easy for the ride to get on and off, making it very particularly for family or commuter bicycle. Overall concept is to combine safety, balance and convenience for user who may ride with children. Finally, let's look at the result and what we can conclude. Our analysis show that concept 3 performance the best overall. The extra tube in the front part of the frame help distribute the rider weight, especially if a child seat is installed. This improve the stability of the bicycle and make it suffer for families to use. This result provide that with full design change, we can greatly improve the safety and comfort of a bicycle. We also provide that FEA is a powerful engineer tools. It helps designer find the critical stress point before spending a lot of money and time on making physical prototype. As the next step, we suggest building a real prototype and testing it under real condition to confirm if the improvement from the simulation match real world performance. Thank you very much for attention. After drawing this concept, we simulate each one using FEA. We apply a rider's weight of 70 kg or around 6.7 Newton to replicate the real load on the frame. We also use a mesh size of 30 mm for the FEA. We is a good balance between accurate and simulation speed. Through this simulation, we clearly see where stress was highest on each frame design. Usually, the weak point appear near the seat tube and top tube connection, because this area carry the most load and experience the most bending. Thank you for the.
This is the free body diagram of the bicycle on a flat surface. So we can see that the fixed support is located at the bottom bracket area, which is the main structural connection to the ground. The weight, or we know as W, of the bicycle and rider acts vertically downward through the center of mass, generally near the seat tube. So since there is no slope, no additional horizontal forces is acting, so the ground provides a reaction force upward, also a horizontal reaction if necessary to prevent slipping. So the key points to this free body diagram on flat surface is the vertical weight force, the fixed support providing vertical and horizontal reactions, equilibrium in both x and y directions. In this diagram, the bicycle is climbing an inclined surface, so the weight still acts downward, but now part of it creates a component along the slope which causes the bike to slide backward. To prevent this, a forward force, or F, is needed, usually provided by the rider through pedaling. The fixed support is still at the bottom bracket and resists both vertical and horizontal forces. So the key points to this highlight of free body diagram is gravity splits into parallel, down the slope and perpendicular components. Rider applies forward force to climb, and support resists motion down the slope. Here, the bicycle is going downhill. Again, the weight acts downwards, but the slope causes a forward component of gravity which accelerate the bike forward. In this case, the rider may apply a braking force to oppose the motion and maintain control. The support reaction again counteracts both vertical and horizontal loads, especially resisting forward sliding. So the key points to this highlight: gravity cause forward motion. Rider or brakes apply backward force to control speed, and also support provide resistance to slipping downhill. So from this table, we can conclude that the first one, for the flat surface, the seat tube angle is 66 degree. Most of the force goes downwards with 627.6 Newton. Smaller part pushes forward with 279.4 Newton. So we can say that it is easy to control and balance load. For the uphill with 10 degree of slope, the seat tube angle is 76 degree, which 66 degree and 10 degree of slope, with less force pushes forward of 166.1 Newton, while more force pushes down, which at 666.3 Newton. So we can conclude that it is harder to pedal, more weight to pulling back. For downhill with 10 degree slope, the seat tube angle is 56 degree, which 66 degree minus by 10 degree. So more force pushes forward, which 384 Newton, while the less downward force is 569.7 Newton. That says it is easier to move forward, which needs better control. So we can summarize as the slope changes, the direction of force also change, which uphill equals to harder to move, downhill is easier to move but harder to stop.
Assalamualaikum, my name is Muhammad Nilukman bin Mat Salihuddin. My number metric is B0922100044. I will present about the finite element analysis FEA results and discussion. This finding reveal how the bicycle frame performs under the three critical riding conditions for flat ground, uphill, and downhill. By examining total deformation, stress distribution, and safety factors, we can assess the frame's structural integrity and identify areas for optimization. Let's dive into the results, starting with the deformation analysis. The FEA results reveals that the bicycle frames experiences varying levels of deformation depending on the terrain. On flat ground, the deformation is the highest at 0.3949 mm, primarily due to vertical loads causing significant bending at the seat joints. In contrast, during a 10-degree uphill ride, deformation will decreases by 40% to 0.23513 mm as the load shifts rearward to reducing the frame flex. The most favorable scenario is downhill at 10 degree, where the deformation drops dramatically by 75% to 0.10002 mm. This is because the weight transfer to handle tube to minimizing deformation and improving overall stability. Okay, next we go through the second results for equivalent stress analysis. The stress distribution across the frame also varied with terrain. Flat ground riding produced the highest stress of 124.78 megapascal, concentrated at the seat joints due to the vertical forces. Uphill conditions show 35% reduction in stress, 80.49 megapascal as the drivetrain shared the load more evenly. Downhill riding exhibited the lower stress levels at 37.46 megapascal, 7% lower than flat ground, and thanks to compressive force that followed an efficient path to minimizing von Mises stress. These findings highlighted the importance of reinforcing seat joints for flat ground durability. For the last results for safety factor evaluation, the safety factor, a critical measure of structural reliability, was lowest on flat ground at 2.00, indicating stress concentration that reduced safety margins. Uphill conditions improved this by 55% to 3.11 due to better load redistribution. Downhill riding offered the safe scenario with a 234% increase in safety factor, 6.67 as compressive loading enhanced frame resilience. This underscored the frame's robustness in downhill conditions while flagging flat terrain as the most demanding for long-term fatigue resistance. In conclusion, the FEA analysis confirmed that the bicycle frame's performance was highly terrain dependent. Flat ground riding posed the greatest challenge with peak deformation stress and the lowest safety factor, necessitating targeted reinforcement at seat joints. Uphill conditions improved stress distribution and safety, while downhill riding delivered the optimal performance with minimal deformation and the highest safety factor. These insights validated the frame's durability across diverse conditions and emphasized the need for design prioritization in flat terrain scenarios to mitigate fatigue risks. Thank you.